Let's consider the colligative property of vapor pressure lowering. Suppose that we have pure water. Water is a volatile compound and has a vapor pressure at room temperature. Let's say that we add ethylene glycol to the water to make a solution. The solution of ethylene glycol in water has a lower vapor pressure than the original pure water sample. Ethylene glycol is a substance used in antifreeze that boils around 200 degrees Celsius. Water boils at 100 degrees Celsius. Water is a volatile solvent and has a vapor pressure at room temperature. Ethylene glycol is much less volatile at room temperature and essentially has no vapor pressure at room temperature. But the vapor pressure of the solution of ethylene glycol in water has a lower vapor pressure than the original pure water sample. This is because the solute molecules occupy positions in the solution that had been previously occupied by the solvent when the solvent was pure. There are fewer solvent molecules on the surface of the solution than on the surface of the pure solvent sample. The presence of the non-volatile solute molecules on the surface of the solution reduces the rate of vaporization of the solvent. A lower rate of vaporization causes a decrease in the amount of vapor above the solution and a lower vapor pressure for the solution. The difference between the vapor pressure above the pure solvent and the vapor pressure above the solution is called the vapor pressure lowering. Vapor pressure lowering, or delta P, can be found from either of these two equations. The pressure value with the superscript represents the vapor pressure above the sample of the pure liquid. The vapor pressure lowering of a solution is also observed when a beaker of pure solvent is placed in a bell jar that also contains a beaker of a concentrated solution. On the left, solvent initially evaporates from each beaker to fill the bell jar with vapor. On the right, where equilibrium has been established, the liquid level of the solution is higher than it was initially. The vapor pressure from the solution is low. However, the liquid level of the pure solvent is lower than it was initially. The vapor pressure from the pure solvent is relatively higher than the vapor pressure from the solution. Materials naturally mix. The concentrated solution, which is already a mixture, pulls more pure solvent vapor into it to mix even more. Again, the vapor pressure above the solution is lower than the vapor pressure above the pure solvent. Using Raoult's law, we can find the vapor pressure of the solvent above a solution by multiplying the mole fraction of the solvent by the vapor pressure of the pure solvent at a given temperature. In a pure sample, the mole fraction of the solvent is 1. In a solution, the mole fraction of the solvent is always less than 1. Therefore, the vapor pressure of the solvent above a solution will always be lower than the vapor pressure above the pure solvent. When the solvent is the only volatile component in the solution, then the pressure above the solution depends only on the pressure of the solvent. For a solution with a non-volatile solute, we can simply write the vapor pressure of the solution equals the mole fraction of the solvent times the vapor pressure of the pure solvent. So far, we have considered a solution that contains a non-volatile solute that is dissolved in a volatile solvent. Next, let's consider a solution that contains a volatile solute that is dissolved in a volatile solvent. Toluene is an organic liquid that boils around 110 degrees Celsius. Benzene, another organic liquid, boils around 80 degrees Celsius. Both toluene and benzene are volatile. The total vapor pressure above a solution of toluene and benzene is due to both the vapor pressure from toluene and the vapor pressure from benzene. We can use Raoult's law to find the vapor pressure from both volatile liquids. The total vapor pressure, which is the vapor pressure of the solution, is the sum of the vapor pressures of the solute and solvent. Please note that the value of the total pressure above the solution is a value that is between the vapor pressure values of the two pure liquids. Recall that solutions form when solute-solute and solvent-solvent interactions break to allow solute-solvent interactions to form. An ideal solution follows Raoult's law, where the total strength of interactions that break equal the strength of the interactions that form. If the solute-solvent interactions are stronger or weaker than the broken interactions, then the solution is non-ideal. Let's consider three cases. In Figure A, vapor pressure is plotted along the y-axis and mole fraction of volatile liquid A is plotted along the x-axis. When the mole fraction of liquid A is 0, only liquid B is present and the vapor pressure equals the vapor pressure of pure liquid B. When the mole fraction of liquid A is 1, only liquid A is present and the vapor pressure equals the vapor pressure of pure liquid A. Between those 2 points, a solution of liquids A and B is present. The total vapor pressure of the solution is the sum of the vapor pressure of A and the vapor pressure of B. The total vapor pressure of the solution has a value that is somewhere between the vapor pressures of the two pure liquids. In Figure A, the lines for the partial pressure of A and the partial pressure of B and the total pressure of the solution are all straight, indicating that the vapor pressure of the solution is what is predicted by Raoult's law and that the solution is ideal. In Figure B, we see that the lines for the partial pressure of A, the partial pressure of B, and the total pressure of the solution are all curved downward. The vapor pressure of the solution is lower than what is predicted by Raoult's law, and the solution of liquids A and B is non-ideal. The solute-solvent interactions are stronger than the solute-solute and solvent-solvent interactions. The downward curves indicate negative deviations from Raoult's law. In Figure C, we see that the lines for the partial pressure of A and the partial pressure of B and the total pressure of the solution are all curved upward. The total pressure of the solution is higher than what is predicted by Raoult's law, and the solution of the liquids A and B is non-ideal. The solute-solvent interactions in this case are weaker than the solute-solute and solvent-solvent interactions. The upward curves indicate positive deviations from Raoult's law.